This is super fun for me to be here. A little bit intimidating to be the first speaker of the quarter, which I didn't quite get in my head when I agreed to this date, or suggested this date. Because I'm a local speaker, I thought I would do something a little bit different than what I usually do. I'm not going to go into as much detail as I normally would if I wanted you to actually understand everything that I was saying. I want to give you sort of some details and some ideas about several things that happen in my lab, with the idea that you can come down the street, walk over to the quad, and talk to us some more if these are interesting. So these are sort of various things that we do in my lab that I think are either interesting or related to HCI, or hopefully a little bit of both. And yeah, let's get into it. So the first thing is to say, what kind of thing do I spend my time thinking about? And why is it that even though I come over here a lot, I'm in the psychology department at Stanford? So here are written down as kind of examples from natural language, a bunch of really interesting ways that people think, ways that people reason. So you might hear, all men are mortal, Socrates is a man, and then people would conclude, so Socrates is mortal. That's a kind of reasoning argument that people are happy with. You might also hear, most men are workers, most workers are busy, so most men are busy. To us, that seems like a pretty good argument. And if you ask people, if you go crowdsource it, do experiments, people will generally endorse that as pretty good. It's different because it's not logically valid. So the systems of deterministic logic aren't going to say that that's a good conclusion. So that already sort of shows where there's a kind of genuine psychological question of how to account for the kinds of inferences people draw that our formal systems don't. You can go on and make it more interesting. Imagine a game football. Imagine that Bob beat Jim at football. You might conclude that Bob is a strong football player. But if you also know that Jim is the weakest football player, then you probably no longer think that Bob is strong. You think he's an average football player. So this is an example of kind of graded defeasible reasoning. Or something I'm going to touch on briefly as I go. I waited 1 million hours for a table at that restaurant. Probably doesn't mean that you waited 1 million hours. It probably means you waited longer than usual and you're annoyed about it. Right? So accounting for these kinds of inferences that people draw is the kind of thing that we think about in my lab, particularly sort of one corner of my lab. The other corner is we work on probabilistic modeling and AI. And probabilistic models, how many of you have never heard of probabilistic models? Okay, a subset. Oh, a significant subset. Interesting. Okay. So probabilistic models are a kind of representation structure that's come from statistics and mathematics, and that's kind of taken the world of machine learning, AI, computer vision, NLP, all of those sort of that part of computer science by storm. I'm here representing sort of in low resolution two different kinds of probabilistic models that people use. On the one hand, there are probabilistic context-free grammars, which are models that describe how to get different trees, like that tree that says book the dinner reservation or something like that. And they're written down with these derivation rule kinds of structures. Over there, I'm representing what's also a probabilistic model, but that looks very different. That's a mixture model that describes the mixture of sort of two latent kinds of things with some observed continuous properties. So there's two things I want you to know about probabilistic models for understanding the rest of this talk. One is that they're incredibly powerful, and they're powerful anytime that what you want to capture is you want to be able to represent uncertain knowledge and then describe what are useful ways to reason over that uncertain knowledge. That's why they've taken the world of machine learning and AI by storm. The other thing I want you to know is that the tools that we generally use to specify those probabilistic models are a complete mess. It's incredibly heterogeneous. That's what these pictures show you. We use some, special purpose little representations. We use some math. We use some English. We use some diagrams and pictures. And as the models get more complicated and more kind of realistic, it gets harder and harder to write them down. So the first thing that I want to tell you about is something I started thinking about 10 years, basically because 10 years ago, basically because I was building psychological models using probabilistic modeling tools, and they were very hard to write down and very complicated. And I thought there must be a better way. And then I went and realized, well, in fact, computer scientists know how to write down knowledge in a very flexible, formal way using computer languages. That's the lambda there. But what computer languages don't do is represent uncertain knowledge using probabilities. That's the P of H given D probability there. So we started thinking about probabilistic programming languages, which are basically just a merger of those two. They're a way to write down probabilistic models using the tools of programming languages. So the first thing I'm going to do is tell you very briefly a little bit about probabilistic programming languages, give you sort of a pointer to some places that you can learn some more. And then I'm going to show you an example of cognitive modeling using these languages. Then we're going to go on to do some other fun things, but we'll get there. OK. So what's a probabilistic programming language? Well, the idea is we're going to build some formal language for describing probabilistic models, starting from a universal programming language, C, Java, in our case at the moment here, JavaScript, Lisp, whatever you like. And we're going to do that by starting with the programming language, the deterministic part of the language, adding primitive functions which are random distributions, things like flipping a coin or drawing from a Gaussian distribution. Adding these two operators, sample that actually does the random sampling, and factor which upweights or downweights a particular program execution, says this one looks good, this one looks bad. And then marginalization. These are the conditional inference operators that actually describe reasoning. So in particular, I'm going to describe this to you in a language that we've been calling WebPeople, WebPPL, which is a small probabilistic programming language that's built on top of JavaScript. So it looks like JavaScript when you write in it. It's a subset. It's the purely functional subset for technical reasons that I can tell you about later. What we have in this language is several different sort of algorithms for inference, algorithms for reasoning. I'm not going to get into too much the details of how these work in here. We're just going to assume that they do work. And you can ask me later on or take a look at the things we've written. They have markup chain Monte Carlo, particle filtering, and some slightly clever search strategies to sort of actually implement the reasoning. What I like about this language, oh, by the way, it's pretty preliminary. We implemented this language about a month and a half ago when I had to teach a summer school class. And we thought, hey, why do the easy thing of using a language we have when we could write our own brand new one again? Because, yeah, that's the thing to do. So the thing I like about this language as opposed to the other probabilistic programming languages that I usually use is that because it's sort of looks like JavaScript and is implemented in JavaScript, you can use it for sort of directly embedding into web apps, which is something I'm going to try to come back to at the end, something that I want your guys' help with, the HCI community. It's also a pretty good compilation target for other languages. It's a nice, simple little language that you can compile to. So we have a set of notes at dipl.org on this language, and I'm going to now jump over there to sort of show you a little bit about the language. Hopefully my Wi-Fi will work, otherwise this could be disastrous. So if you go to dipl.org, oh, right, this is why I had it mirrored. OK, at the risk of crashing everything. Yeah, oh, OK, working so far. Good. OK, if you go to dipl.org, you'll see this, which is our sort of set of notes, a little web book. And it, in case you're interested in how these probabilistic programming languages actually work, you can just go read this. That way I don't have to actually tell you about it in the course of this. I can tell you what you do with them. The language that we talk about in these notes, WebPeople, basically it's got the usual bits that you would have from JavaScript. So this is the most boring program you can write with the parts of JavaScript that we have, using pretty much all of the parts. So we can define functions. We can assign variables by calling external functions like math.exp. We can do conditionals. So this says if x is 0, be empty, otherwise stick. Do recursively call foo and stick that onto math.log of bar. Anyhow, so this is the boringest thing you could do. The point is, it just looks like JavaScript to start with. But then we start adding random sampling. So Bernoulli ERP is a primitive object that represents a coin flip, a Bernoulli distribution. And if you run it, you get a random value. OK, so this is just like using a random library. The interesting thing is that if you take a distribution, we have these operations that will compute inference, the marginal distribution. So what that does is it says, look, here's a complicated computation, right? Binomial, which is a function that flips 3 coins and adds them up. I don't care about the flipping the 3 coins. I only want to know how likely it is that I'm going to get 0, 1, 2, or 3. So enumerate says compute those probabilities, and I get some nice little distribution, right? And that all happens under the hood. We can then say, well, what if I want to provide some observation, some additional constraints or knowledge? Like I want to say that actually I want to upweight the executions where A or B is true and downweight the other one. So this one says, check whether A or B is true. If so, I'm going to add 0 to the log probability, which means leave it alone. Otherwise, I'm going to add -2, which means downweight it, right? And now I can use the same thing, the same operation that computes the distribution, and I see, oh, I biased it. Now it prefers getting 2 or 3 over getting 1, right? OK, so now you know the elements of a probabilistic programming language. The reason this looks very simple, right? There's nothing much going on here. I mean, under the hood, there's a lot going on, but there's not much going on. The reason these are cool is because you can now start to write down sort of more complicated pieces of knowledge. Here's the causal structure I think should happen. Place constraints like, what if I sampled 23 things and I observed that 10 of them were true? Right? And you can start to sort of use that to do reasoning, to say, OK, so is the third one true? Or the example that I'm going to come back to at the end, let's say that I had a whole bunch of users using a website and I observed where they clicked. And then I want to write down the probabilistic program that says there's a certain number of types of user. Each type of user has a tendency to click on certain places. Here's a new user. Which type are they and where do I expect them to click next? Right? And having these tools, you can just write those sort of things down. OK, so this is the point where if I were giving you technical details, which I'm not going to do, I would tell you a little bit more about how inference works and sort of show you a small set of examples building up. Instead of doing that, what I'm going to do is jump on into a psychological example of some interesting data that we get from doing a psychology experiment, and then how we use these probabilistic programming language tools to model that data, to come up with a model of what people are doing. So this is from a paper Mike Frank and I published a few years ago, have been working on for a long, long time. So we borrowed this idea of a reference game from, actually from David Lewis in philosophy, the philosophy literature. So the idea of a reference game is that there's 2 players, the speaker and the listener. The speaker wishes to refer to one of those shapes. So imagine you're talking to somebody and you want to refer to the middle object. Are you going to say blue or circle? So there's the middle object. How many people want to say blue? How many people want to say circle? OK, that's good so far. Mostly awake. The listener role is sort of the other side. Somebody uses the word blue to refer to one of those objects. Which one are they talking about? How many people think it's this one in the middle? How many people think it's this one on the side? OK, so now you're still awake. This is a little bit less obvious. It's particularly less obvious if I didn't sequence the speaker and listener in that order. Because, of course, blue refers to the middle object. I could call it blue. It's only that I had a better way of talking about that middle object so that it seems less likely that I would use blue to refer to that one. I don't have a better way of referring to the one on the right. So this is what's often called kind of Gricean or pragmatic reasoning in the linguistics and psychology literatures. And so Mike and I sat down and thought, how can we formalize that? Because there's a lot written about this, but almost no formal work that actually sort of gives a computational model that could draw the right inferences. So here we start with a literal listener. And this literal listener is just a function in WebPeople that takes in a property. So you hear some property like blue. And what this says is, OK, I'm going to figure out the distribution on the object. So at the end, we return an object. And the distribution comes from first saying, OK, the object comes from some prior distribution on objects. We don't know what that is. We'll have to measure that. And then adding this factor that says, look, check whether the object that I just imagined has the right property. If so, it's fine. Otherwise, downweight it to negative infinity, meaning get rid of that object. It can't be that one. Question.
I don't quite understand what this factor function does. Is it mutating some state somewhere? Like, what's going on?
So behind the, let me describe it semantically and then conceptually. So think about, this is where I probably should have given you these details that I decided to hide under the rug. So think about, this defines a distribution on executions of the program. At the end, we're just interested in the distribution on return values, right? And so what factor literally does is it says, look at the execution you're working, you're computing when you get to the factor, and upweight or downweight that execution by the amount that factor is called on. So in this case, if the object has that property, you upweight or downweight it by 0, meaning you leave the probability of that execution alone. If you find out that the object doesn't have that property, you downweight the probability of that execution to negative infinity. You say, actually, get rid of that execution. It should never happen. The tricky thing is efficiently doing that in such a way that you reweight without actually, well, in this case, I am enumerating all of them, but in general, you don't. So yeah.
Could you have multiple factor statements inside that?
Yeah. So the cool thing about this is that it's really a full power Turing complete programming language where you can do anything that is you can use these constructs in anything that's syntactically in any way that's syntactically well defined. You can put a factor statement wherever you want. You can put sampling wherever you want. You can do recursion. You can do all of these things. Yeah. Okay. Here's the deal, though. This function just defines the thing that gets rid of any object that doesn't have the property and doesn't do anything else, right? So this is the cartoon, right? We get rid of the one object that's red and keep both of the objects that's blue. So that's not what we want. The next step, which is where it starts to get interesting, is we say, well, following these philosophers, language understanding is really a social reasoning process where the speaker is thinking about the listener and the listener is thinking about the speaker. So first, let's imagine a speaker who's thinking about the literal listener that we just described. So now we're going to capture that by another function. It's a function where you pass in a particular object that you want to refer to. And it looks very much the same. You say, OK, first sample a particular property description that I could give from just some prior that says uniformly, say, red or blue or square or circle. And then I put in another factor which simply says, take the literal listener. So imagine the literal listener who hears that property. Take a sample from their distribution. So the literal listener imagines one of those objects that is possible. And then we put in a factor that says that has to be equal to the object that I'm actually trying to convey, right? So is the object equal to what the literal listener would imagine? If so, you don't change the probability. Otherwise, you turn the probability down to 0. So negative log probability is the sort of currency. That's why it's negative infinity. OK. And then at the end of the day, we just return the property, right? So it works basically the same. So now that guy's going to think, I want to refer to the middle object, to the left object, let's say. If I use blue, there's some chance that the literal listener will imagine the right thing. So I'll just go ahead and say blue, right? If I had said square, there's also some chance that they would imagine the right thing. So I could say square, right? I shouldn't say circle, and I shouldn't say red. OK. Now we're going to make that fancier, and we're going to say, OK, now let's do the crucial step of imagining a pragmatic listener who is not conditioning on the words being true, but is actually saying, what does it mean if the speaker chose to say those words? Okay, so this has the same structure. You sample an object from some prior, except that what you have in the factor statement is something that says, if a speaker was trying to convey the world I'm thinking about, would they have actually said that utterance? Right, upweight or downweight it. OK, and now you have a listener who's going to think about the speaker thinking about the listener. So I'm thinking about you thinking about me. What's really cool about this is that these are 3 almost trivial functions. But they're, the structure is a nested, sort of nested recursion, right? pragmatic listener thinks about the literal listener, thinks about the speaker, thinks about the literal listener. That makes it a really kind of subtle probabilistic model that, believe it or not, you can't write down with the usual tools. You can sort of fake it with math, but it gets very confusing, and you usually have the normalizing constant in the wrong place. I know this because my students almost always, when they try to work it out by hand, put the normalizing constant in the wrong place. But we've just written it down in a very nice way because we have this declarative language. OK, so then I now take off my computer science hat and I put back on my psychology hat and I say, well, that's going to make some predictions about how people should interpret a particular utterance in this reference game. Are they right? So the first thing we have to do is say, well, I didn't tell you where the reference prior, the prior over which object it is, comes from. So we better go measure that experimentally, right? So we do an experiment. And we do an experiment where what we're going to do is measure speaker interpretations, listener interpretations, and this reference prior thing, right? So the speaker version is there's 3 objects. Imagine you're talking about one of them. Which property do you use, green or striped? Okay. And we do all of the possible contexts of 3 objects with 2 properties, 2 dimensions. The listener is just like I showed you. It's imagine somebody uses the word dotted. Which object are they referring to? And then to measure the prior, how likely it is somebody would talk about a given object, we do the same thing, except we say, imagine somebody is talking to you and uses a word you don't know, or in a different version, a word you don't catch. Which object are they talking about? So that's a kind of measure of a priori, what would somebody be talking about?
So what is that prior, roughly? Is it based on position?
No, it's sort of kind of complicated. It's sort of based on some colors are more salient. It's a little bit about position. The odd man out tends to be good to talk about. So like, you know, the green one on the right here would probably be good to talk about. There's a lot of weird things in there. We get rid of a lot of that by counterbalancing everything, but there's still some stuff that we just, you know, kind of haven't ever bothered to try to make a theory of, so it's much better to measure it. This is where we're similar to HCI, I think. You know, go measure everything with people and then plug it in where you needed it. Yeah. OK, so now what we have is the prior we need so that the model will make predictions. And then given that, it's going to make predictions about how people should respond in the speaker and in the listener cases. And by the way, we did this on Mechanical Turk with, you know, about 1,000 people in the experiment because we wanted to get it right. And it was noisy initially. So here's the overall results. I'm showing you the model predictions for the listener and speaker conditions versus the actual participant responses. In this version, we had participants respond with a bet, place some bet on which object it is. In another version, we did a forced choice, and it's not that different. And the cool result is we can explain people's judgments and kind of behavior in this reference game really well. So we explain 98% of the variance. It's also kind of important for sort of theoretical reasons that it's not like just people always choose the same object. So it's not, you know, people are not at 0 or 1. There's a real gradation that goes on in how people make these judgments and people's understanding in these games. And so being able to actually capture that gradation is the important thing in the model. OK, so we can then try to soup this up. And I'm not going to give you the details of how to soup this up for the same reason. But we extend this to sort of a more complete model of language understanding that these days we call the rational speech acts model. And the basic structure parallels exactly what I just showed you for the reference game. Except the literal listener, we basically start by saying, look, whatever sentences are, they have a literal meaning. And we can treat that as something that you can put into a condition, right, that factor statement. And that lets you update your prior beliefs into posterior beliefs. Whatever you believed before, if the literal listener hears this sentence, they'll update their beliefs and believe something else. That's where we get started in this pragmatics, because then the speaker says, look, I'm just trying to figure out what to say such that the literal listener will update their beliefs to the right thing. And the pragmatic listener is the same thing that we saw. They say, what's the world like, assuming that the speaker chose this utterance, right? What is it that the speaker intends to communicate? We can do a lot of things with this, which is really neat. I'm not going to show you in detail any of these, but we've sort of applied this framework in its basic form or slight extensions to various phenomena in language, scalar implicature and adjectives like tall and big, communicating using prosody, like Mary went to the movies, means that Mary and nobody else did, this kind of thing. The one thing that I will go ahead and mention, because I'm excited about it, it's pretty recent, is extending this to model hyperbole and these other figurative things in natural language. So, for instance, a latte at that hipster place cost $50 is interpreted as not that it actually cost $50, usually, but that it costs a fairly large amount and the speaker is sort of annoyed or is expressing a strong opinion about that. Funny thing, this used to be a latte at that hipster place cost $10, and then I was giving this talk in New York, and people were not convinced it was hyperbole, so I had to increase the price significantly to make it hyperbolic. So what we did here, there's some modeling component, of course, that extends that basic framework slightly. Then we did an experiment where we first measured some background knowledge, and then we gave utterances. We said, Eric bought an electric kettle. His friend asked him, was it expensive? And Eric said, it cost $10,000, where we systematically manipulated both the category of the thing and the price. Right? We varied the price. And we did this on Mechanical Turk with, I guess this was 120 people. And just to make the long story short, this model, this kind of framework is actually, again, able to account for people's interpretations. And here it's a much more challenging task. It's not this sort of artificial, super artificial, 3 objects, which one is it? It's somebody says a description using a number. What's the actual price, right? Do you interpret it as literally that's the price? Do you interpret it as less? And not just do you interpret it as less, but exactly what price do people interpret it as? And the model predicts the data pretty well in this case. Anyhow, and there's a bunch of additional results of this flavor. So if you're interested in this kind of thing, come talk to us. We have lots of work ongoing and lots of more ideas that are yet to be explored. This would be a good time to ask a question before I move on to the next thing. Yeah?
I'm reading Daniel Kahneman's book, Fast and Slow Thinking, and he's talking about basically how inaccurate the rational agent model is. So is there, is it possible to kind of incorporate their prospect theory into this thing?
So this is a good but complicated question. So there's part of the reason it's complicated is because the classic Kahneman and Tversky work, they do a bunch of really cool experiments that show a bunch of biases where the way that you think people should interpret the experiment and answer according to kind of, the obvious statistical, the obvious probability thing is not how people answer. People systematically answer some other way, so there's a bias in reasoning. And then they come up with a bunch of heuristics, which are sort of potential algorithms that could do that. It's complicated for me to respond to that because it's quite heterogeneous. If you look in detail at all of the different biases, it's probably not the same thing going on in each of them. So some of them, like availability, are probably very reasonable probabilistic algorithms where it's hard to get the prior probabilities, so you use as a proxy how easy it is to remember a thing. Others are actually probably exactly the sort of effects that I'm accounting for rationally, that they're pragmatic context effects. So for instance, the conjunction fallacy, where you say, sorry, this is going into some detail. For those of you who don't know it, ask me later. But the conjunction fallacy, you provide a whole bunch of extra information. So, Sally was active in the feminist movement in college and always, buys organic granola and these things. And then you ask people, how likely is it that she's a bank teller versus how likely is it that she's a feminist bank teller? I shouldn't have said feminist in my description, and people say, oh, she's probably a feminist bank teller, and of course that's an error because you shouldn't ever say that A and B is more likely than just A alone. So bank teller, feminist, and bank teller. What's weird about that, if you think about it conversationally, is why is the experimenter giving me so much information about Sally if they're not implying that she's feminist, right? I don't know anything about this bank teller thing, but they just told me all of this stuff. Why did they tell me that? So my response is basically to boil it down to a very small thing, is that those phenomena are real. Some of them are actual things about cognitive processing that would be kind of corrections or would be we would want to include. Others actually are really about the experimental context. And so us Bayesian cognitive scientists wouldn't necessarily say that people are doing an irrational thing. We would say that they're doing a very reasonable and maybe kind of probabilistically correct thing given their interpretation of where this data is coming from. Like, why is the experimenter asking me that question? We can talk more about that for sure. Other questions before I switch to something a little bit different? Yeah.
Trying to think through how good people are at estimating someone else's mental state. Because that seems like a strong assumption of this recursive model, where I'm thinking, what would a speaker who meant that do?
Yeah.
And certainly there are a lot of reasons I could imagine why I'm really poor at this, and that leads to a lot of flaming on email lists, for example. Are there ways to fuzz these assumptions of what such other person would do in such a way that it can account for this?
Good question. So I didn't say too much. I didn't talk about this in too much detail, but these are actually automatically already fuzzed because. So what this actually gives you, like for the speaker model, for instance, is a speaker who only chooses their action softmax optimally. So there's a small chance that in proportion to sort of the prior probabilities here, that they're going to say not the optimal utterance. It's a little bit obfuscated in this representation, but we can kind of walk through it. So you rule out all of the descriptions which are actually false, right? Of the descriptions which are left, some of them, are slightly better due to a prior, in this case, but other things in other cases. The optimal thing would always be the highest probability thing that's left. Always say that deterministically. That's not what this model does. This model will say things in proportion to the probability after including that factor. So in some sense, it's already a little bit accounting for the fact that actual actors are not optimal. That's not so that's like a version of fuzzing it up, which actually is completely crucial. Without that, you predict very much the wrong things for these experimental data. It's likely that there are other effects that in much more complicated situations, people degrade at how good they are at guessing other people's intentions. There's two things we have going for us in these experiments. One is that even the hyperbole one is sort of a relatively restricted case. But two, and I think much more important, is that we're studying basic language understanding things that people have a lifetime of practice at. People, are very good at the basic operations of language understanding because they do it all the time. And so, even though those inferences can be hard, I think they're kind of cached or something that makes them pretty accessible. I'm actually kind of interested in pushing the boundaries and seeing where those break down. And I suspect it's not going to be for these basic operations of, kind of understanding language, but it's going to be much more in these situations where our interests are misaligned or potentially misaligned. The reason I think that is because cooperative games tend to have a dynamic where I think that you think that I think converges. It could take a while, but it converges pretty monotonically. Competitive games tend to oscillate wildly. They might eventually converge to a solution, but they do so by oscillating back and forth. And so I think you're more likely to find those errors in reasoning about other people in those more competitive situations.
Cool. Thank
you. Yeah. Other questions? Okay. I wanted to mention another very different thing, also sort of deriving from the idea of probabilistic programs, because I think it makes contact to some things that HCI people also do, and it'll be interesting to find the connection here. So let's imagine that I've made the leap of representing my theories about how people behave as probabilistic models, like I was showing in the last slide. And now I'm doing science. I'm a good scientist, and I want to posit several theories and do some experiments to test them, right? I want to say, here are my three theories. They're sort of three sketch toy theories about the relationship between X and Y. And now what experiment should I do in order to distinguish the three theories, to decide which is the right theory? Of course, if we are good Bayesian statisticians, we say, well, look, the three theories predict different response distributions. So I want to think of this as X is the prompt I give to subjects, and Y is their response, right? So I give them a red circle, and their response distribution is one thing. I give them a blue circle, and their response distribution is something else. And those response distributions differ between the different models. So we can then sort of make a formal attack on the question of which experiment we should do, which basically amounts to which set of prompts should we give subjects in order to gain the most information about which of these distributions is actually a good description of their responses. So here's a slide full of math that I won't talk about the math in too much detail. We start by basically saying, OK, if you saw some data, you know how to update your beliefs about which model is true. You sort of upweight the models that would have predicted that data and downweight the models that wouldn't have predicted that data. And Bayes' rule describes that. We can then say, OK, now that means we have a prior distribution, our prior belief about which model describes people, and our posterior after seeing the experiment. And so we can measure the difference between those. A good measure of the difference between distributions is the KL distance. So we say, look, the amount of information I got from that experiment is the KL distance between my prior beliefs about which theory is right and my posterior beliefs. Of course, that's only after I see the data. So before I see the data, the best I can do is compute how much information I expect to gain if I see the data that I would expect to see. So we can get the expected gain in information, which is just the expectation over that KL distribution, KL distance. And then the optimal experiment, we can say, is the one that gives me the greatest expected change in information, the greatest expected gain in information. So we take the argmax over stimuli of that quantity. OK. That, if you know the words I just said, is kind of fairly obvious. And if not, the point is we can just formalize in a straight way how much information I expect to gain from doing an experiment if we've already phrased our different theories as probabilistic models. OK. So we've implemented this in a kind of pretty straightforward way. So our current system just takes a set of probabilistic programs, which are the candidate cognitive models, a predefined set of space of experiments. Those are the potential stimuli. And also a linking function that describes sort of how people are going to use the actual response distribution. So people get a belief distribution, but we actually ask them for a forced choice or a Likert rating or a slider or some other crazy thing. And we need a function to link between those. And then the system just goes and it actually exhaustively enumerates the space of experiments, which is not very smart. That's very inefficient, and computes the expected information gain for each one to decide what experiment should we do. Is that clear? OK. So for example, I want to give you an example of this sort of in practice. This is the one example that we've actually finished so far. This is very much in progress. This is a classic category learning experiment. You show people a card with a shape, and you say, is this an A or a B? They click one of them, and you say, correct or incorrect. Might ask them, how meaningful is this word? This is an interference task so that they sort of don't know what's going on, basically. Show them another card. You might both ask them if they've seen it and which category do you think it belongs to. And you keep doing this as they learn the category, sort of going along. So this is, we did that particular format because it's the one used in this classic 1978 paper. It's a paper by Medin and Schaefer, where what they set out to do was test between two theories of categorization, what's called the context theory and the independent cues, or exemplar and prototype. And you don't need to know actually what those two theories are. One of them basically is a sort of kernel thing where you put a bump, a generalization bump on each observed exemplar, and the other sort of pools together and puts one Gaussian over that best fits the exemplars. The thing you need to know is that these were two theories of category learning that were being argued about in 1978. And Medin and Schaefer designed the canonical experiment to distinguish them, which was that. The important thing, actually, there's nothing terribly important here, except they thought about this really hard and came up with this set where there were 5 things in category A and those 4 things in category B. And they ran this experiment, and they used it to tell the world that the exemplar model was a better model of human categorization. We can compute the expected information gain from doing that experiment in our framework and find out that we expect to gain about 0.3 nats, whatever, some unit of information, natural bits. So we expect to gain a certain amount of information a priori from doing that experiment. Then we can ask the question, how good is that compared to all the other experiments we could do, right? So you might think, I thought, hey, Medina and Schaefer were really good psychologists. They probably designed an experiment that was well above average in terms of expected information gain from doing that experiment. So first, here is the distribution on expected information gain across the, I don't know, 100,000 experiments or so that we evaluated.
And the possible experiments here, sorry, were just different ways of splitting up A and B?
Yeah, basically just different objects, 5 objects that would be A and 4 would be B, and which objects should they be? Yeah. So turns out expected information gain is roughly Gaussian in distribution. That's fine. Here's where the Medina and Schaefer experiment is, right in the middle of the bunch. So it's average in information gain. The optimal experiment is way down here, right? So then we could do a fun thing, which is, great, there's the optimal experiment. There's the Medina and Schaefer experiment. Let's run them and see if that is actually a better experiment. So we ran them. And a priori, what we expected was that we had an expectation of 0.3 nats from the Medina and Schaefer and 0.46 from the optimal experiment. And what we actually got from running the experiment and then updating our beliefs in the models was 0.22 nats from Medina and Schaefer and 0.43 from the optimal experiment, right? Which is amazing. It's amazing both that the optimal experiment actually did give us more information. We could more confidently conclude that the exemplar model was the better one, and that they were that close to what was predicted for the information gain. That didn't have to turn out that way. That was kind of a surprise, right?
You concerned about 22 versus 15?
No, this is just because we ran it as a single hit that randomly assigned subjects, and with Mechanical Turk, it's hard to balance. So basically, no, it was not pre-planned that way, and it wasn't that we saw it didn't work and increased the subjects. It was that we got.
Well, sure, but I mean, that's still like a lot more people, right?
22 versus 15. Not
There's some amount, not enough maybe to explain all of that, but
yeah. Oh, I should tell you, right? If we collapsed the response distribution into a single distribution before we updated the information gain. So you don't actually get extra sort of observations from the 22. Sorry, that's important.
Okay.
That's an important reason I don't worry about that.
Yeah. Okay.
Yeah, basically reweighted, or kind of did a kernel smoothing to get the implied distribution as opposed to the individual things. Right. Yeah. Right. I didn't say that, so that was a very good question. Okay, so the takeaway point from this, I think, is one, there's a takeaway point for kind of empirical science, which is actually as you start to formalize your theories, and then you do some computer science thinking, you get access to these additional tools that I'm calling these Bayesian power tools, that in some sense we're doing the same thing. We're designing an experiment. But instead of doing it sort of the old-fashioned manual way, we have this big power tool, right, that just lets us sort of sort through this space of several hundred, 60,000, 100,000 experiments and find one that is expected to be pretty good. And I think this is really actually very promising. I also think there's a really interesting tie-in to what people need to do on the web for kind of website interaction issues. So people use A/B testing all the time, which is really a kind of online experimentation to determine the website. As the sort of space of options gets bigger, just sort of randomly doing an A/B gets sort of less and less informative. And I think this sort of tool, this sort of framework could be sort of extremely useful at choosing, like, I want to learn a model of my web users. Here are the things I'm considering. Which websites should I serve up and compare in order to best distinguish what my users are actually like? Right. So this is a breadcrumb for something that I could talk about with people who are interested in that kind of thing in the future. Any questions?
Okay. Oh, yeah. How easy is it to scale the number of parameters? So like if you're doing a web page, one of the problems is, right, you color, size, locate. There's so many different degrees of freedom, right?
Yeah. So this is a good one about conceptually it's easy, meaning the space of possible experiments, right? The way we have done it right now, we're enumerating, and so we just exhaustively explore all of those. So that doesn't scale. On the other hand, there are lots of it turns into a black box optimization problem, right? We have this function that we're trying to optimize that goes from experiments or web pages to expected information gain, some real number. That's just a black box that we can run, right? And so now you can use any optimization algorithm that you like. We haven't done much of that yet, but it feels like a space where throw your favorite LBFGS, Bayesian optimization, evolutionary algorithm kind of thing at it, combinatorial optimization, and just see what works, right? Particularly, I would be worried about that if the goal were actually to always find the optimal experiment. It might be just hard to find. But if the goal is more sort of practical of finding a good experiment, I think any optimization algorithm that's worth its salt is going to help us find a good experiment much more easily than if we tried to do it by hand or by random, just a random guess.
Sorry, this isn't going to obviate the need to actually consider the space of experiments and design that.
Exactly. That's why I kind of talk about it as a power tool rather than a magic bullet or something, right? Yeah. You're doing the same thing. You still have to sit down and design the space of experiments. It just lets you get much more quickly to a good experiment in that space, right? In principle, you can also do an automated cycle where you take the results of your data and automatically find a next experiment to do. But yeah, so it facilitates the task that you had at hand already. So it's sort of I guess the other way of thinking of this as HCI, maybe which is a better way, is that, we're trying to augment the scientist and give them tools that help them do their job faster and better, right? And this is kind of like, if this worked in my vision of this, it would be an amazing way of buddying up a psychologist with his computer to do better psychology.
I mean, this is an interesting perspective because my experience with industry has been that most A/B experimentation and online experimentation is sort of atheoretical. Mm-hmm. Hunch-driven would perhaps be a more fair way to describe it. It's like, we want to get more click-throughs on this thing. Well, maybe if we make it animate and shake a little bit, or well, that didn't work. What if we increase the font size or move it over here? And it's this very iterative process of over time discovering what your model is of your web user. Mm-hmm. So it's almost like you have these three models, and it's almost like model 1 and model 3 were the ones that are trying to distinguish between. Of course, this will cause that behavior to happen more. No, actually, there's some other variable that I don't even know about, haven't been thinking about. So I feel like from what I've seen, that's really trying to speed that iterative process, maybe preventing me from getting into I should just get more users into this thing, or actually no, you're wrong, just move on, consider something like this.
Yeah, sort of automated tools for designing and interpreting the ways to test your hunches.
Yeah, although, another problem is that there's very, very little knowledge transfer across experiments. You have this team that tries to, bold the text on this part of the page, and they found something, and then this team that tries to do something similar. So they just redo these experiments all the time because no one knows.
Yeah.
But this might be an opportunity, especially since on the web you have sort of a closed set of possible operations in CSS or whatever, that you could build up these priors of what might be happening.
Yeah. I think the real, this is really what you're highlighting, that the real gap between this and, say, people in industry doing stuff on the web as opposed to a working psychologist is the need to have a model of the user, an explicit model of the user, right? Which they won't have. And so the question is is there a sense in which you could make a tool that has, a bunch of, or a parameterized model of the web user, right, where the particular parameters you need for one website are different from another, right, and then use this to kind of rapidly figure out which user uses my website, which kind of user.
I think what you're suggesting isn't bad. Like, one thing we know from prototyping theory, not your prototype theory, like the Scott Clemmer style, like make multiple prototypes, right, is that that's forcing you to articulate different perspectives, hypotheses, sort of about like, well, maybe this is the right design, or this is the right design, or this is the right design, because the hunch that people often operate on is like, oh, it's got to be that. Like, I've been working with PMs in the past where they're like, yes, just animate that thing out. It's got to be it, and then it doesn't work. Like, well, maybe you got to animate it faster. This happens. But if you force people to articulate a large set of options initially, I bet you'd end up with better websites. So I wonder if there's some way to produce like the benefit, such that if you've done this now I can run your or whatever it is, A/B test, set of A/B tests, and get you to where you need to be.
Oh, yeah, that's interesting.
Just have the page or whatever where it's like, what are your 4 models?
Yeah.
I only have 2. No, what are your 4 models?
Yeah, I mean, you need to provide enough of a benefit such that people don't just be like, no, it's going to be this one. Let's run the AP test. It'll be fast. In reality, it's never fast.
Right. Interesting. Okay, to be discussed.
Yes.
Let me tell you the next unrelated idea that I wanted. This is the one that is sort of an idea we've been playing with, but we don't know quite what to do with it. So I thought that's a great excuse to talk about it, and then you can tell me what to do with it. So this is going back to what I was first talking about, web people, this sort of probabilistic programming language we have. And, well, it's JavaScript, and so it runs in the browser. And all we've been using that for at the moment is making these little code boxes for the tutorial that we can run in the browser. But, hey, what you do with JavaScript in general is make web pages better, right? They do stuff. They're dynamic. They do things. So the idea is, well, we can embed probabilistic reasoning, sort of these probabilistic models and inference algorithms, into web pages now, because we have web people. And so that should facilitate various kinds of smarter interaction, web pages that do smarter things, right? Basically AI for web pages. And in particular, there are things that you wouldn't want to do on the server side because of latency, or sort of overload of your server, or maybe because you have sensitive information or something like that. So we sort of have several possible ideas, which I don't think are exhaustive or particularly good. So one that I'm going to show you next is sort of do some sort of user modeling to guide the interaction that people will have with the web page. Another, which is actually kind of also mashed into the simple example I'll show you, is, well, when you're going to go to lay out the DOM elements to actually generate the web page, there's nothing that says that can't be done algorithmically, and in particular, it can't be done as an inference. Like, given the context and the kind of user, what should my layout be like? There's also sort of ways to use this for doing like distributed machine learning and keeping, doing machine learning processing on sensitive information, but keeping it on the user's computer. And I don't know, you guys should tell me what this might actually be good for. But let me show you an example. So lots of pages have lots of links on them, and they're really annoying. They're incredibly busy. There's like huge set of links, and I sort of vaguely believe that there are things that might be interesting to me in this huge set of links. But I have to actually go and look through them, and it takes forever, and it's boring. What we'd like is that the most interesting links should be the most salient, the brightest, or the ones at the top, or something like that. The problem with that is that different users are interested in different things, right? So somehow what we'd like to do is a user goes to this web page, and we sort of know that there are different kinds of users. We figure out as fast as we can which kind of user this is, and we use that to update the web page to present the user things that they will probably find interesting. Basically, this leads to a kind of simple idea, which is let's embed a web people program into a web page, which essentially goes and controls the CSS, or controls the link order or appearance or some other aspects of the page, and let's basically collect interaction data from previous users, what they've clicked on. And then we'll have a model that basically learns types of users by a sort of probabilistic clustering thing. A new user is there and starts clicking around, and we'll update our beliefs about what kind of user that is, which cluster they belong to, and use that to predict what we think they'll click on next. And then we'll make that bigger or brighter or something. So let me, maybe in the interest of time, let me first show you this in action. Hopefully it'll work. So here's a link page that we made up. And first let me show you. So I reload it, and it loads with them in sort of a random order, and it runs the predictor. And then after it runs the predictor, it reorders them. And this is basically now, it doesn't know which kind of user I am, so this is just in proportion to how often previous people have clicked on these links. But maybe I look at this and I think, ooh, dogs using sunroofs. Wow. So I click on that, did it in the background, and now it reruns the predictor, updates its belief about what kind of person I am, and now all of a sudden it puts the things about animals at the top. Cats and pigs and other cats and so on. It's decided that I'm the kind of user who likes animals, right? And maybe I'm not really that kind of animal user. Maybe I also really am into food. So I say, ooh, restaurant horror stories. And I click on that, and then it runs the predictor, and it re-ranks them again. And now there's some food things up there. It hasn't altogether decided I don't like animals, but now it also thinks I like food things, right? And you can keep doing this, and it'll sort of update its beliefs about what kind of user I am and re-rank accordingly. Yeah.
You'd also, I mean, on the initial clustering that you need to do, that has to be done on the server side. I mean,
so this is cool. So there's two things to be said about this. One is, this is a simple enough model that actually we're doing the entire inference, including all of the previous users' data in real time, every time it says updating prediction. There's some details about why that happens. The broader vision is that you would want to do sort of, you'd update the model for each user, having already the state of the learning from the previous users. And then maybe at the end, you'd send that back to the server, right? So that it could be incrementally learning as users used the thing, right?
So do you use a cookie or something on the client side as of now to store this data between reloads?
Oh, there's an important thing I should tell you about this, which is that we made it more or less last night, well, in the last 2 days or so. So it doesn't do anything smart. There's no cookies. This is why I'm opening the links in the background. It doesn't actually remember who I am. We could use a cookie and remember the user.
As of now, if you reload it, just goes back to the default.
Yeah. Because we didn't put that in. We didn't have time. I mean, it would be very easy not to do that, but yeah. So there's yeah.
It seems like this would be super useful to people who have their own web page, but don't want to go through something like going to a big company that ends up helping you figure out what your content should be. I think the main issue is like the values in building the models, like meaning figuring out what actually is more interesting to people. I think that's really hard, actually.
Mm-hmm.
Or you need to update or something.
Yeah, I mean, it's interesting. So there's a couple of really cool things about doing it this way, and a couple of kind of crazy, not good things. One of the things that I think is cool is that, the model is actually kind of a pretty simple, straightforward model in Web People. This is a simple little clustering model. And because Web People is this high-level language for describing these models, I can go and I can twiddle it and do rapid prototyping and change it a bunch, right? So this is a standard clustering model, a standard multinomial mixture model, except that we hacked it up to make it so that it's unlikely that somebody clicks on a link they've already clicked on, which was really important for making this do something sane. You wanted the links you already clicked on to go to the bottom, right? But if I just took an off-the-shelf mixture model, it would have been kind of impossible to add that. And then as I thought about this, you can start just sort of imagining things and doing tweaks and adding your knowledge to it. So one of the value addeds is just, you have this, you can do rapid prototyping of all sorts of different things that the website is reasoning about. What's less good is, like, where does the data come from that it learns from? The ideal version in my head is that it pools over time. So as users use the website gets smarter and better at helping its users. But yeah, would that actually happen? It's actually really slow in general at the moment, so there's some speed things that need to happen for this to actually be useful. Yeah.
I don't think your big win is from a single page. I actually think that you talked about privacy, but like giving me a local way to actually aggregate across all of my web browsing is something that no single server-side solution would really ever be able to do, unless maybe you're one of these like ad servers, but like no one likes those. So my ability to actually
Interesting.
produce a local model of every site where my activity on Amazon can change my BuzzFeed, say, without letting BuzzFeed know too much about who I'm interested in.
Oh, that's a good idea.
Another example that I've actually seen in the literature, and then I'll shut up, is Julia Schwartz at CMU, who's used this actually on the input side. So you're thinking about now things, why would you want this to be done locally? So on something like a tablet or a phone, what she's been doing is using these kinds of probabilistic models to figure out what is the thing that you actually tapped on. You have this big space that you've just covered with your finger, and based on our knowledge of what might be happening, it can sort of trigger different listener functions. Probabilistic.
Right. And in general, kind of the latent model that I have here goes back to the social cognition stuff. That's why this is not totally different. Of like, we know that people are constantly maintaining and updating beliefs about what other people's goals and beliefs are, right? Why shouldn't web pages do that, right? Why shouldn't my web browser keep track of like, what's he trying to do, right? And then there's various ways that the web browser could help me. Maybe reorder the links.
So it lowers its opinion of you when you go to BuzzFeed.
Yeah, probably. It's not judgmental. It doesn't have a. Okay.
It's just a dimension. It's a feature.
Yeah, right. You're just that kind of person. By the way, this is more or less the end of my content, so that we can consider this the general discussion.
Questions, chat.
I'll put that there. It says there's some resources you can go to learn more about the sort of things we do, and if you have ideas, you should tell us. So maybe I'll go in this rough order.
Sorry if I'm being repetitive here, but one thing that I would imagine immediately whenever you talk about reordering stuff on a website is people just don't like it.
Yeah.
However, there's a lot of ways of getting the same benefit by doing things.
Andreas thought that, so
subtly.
he made one that actually just changes the opacity. Oops, sorry, that's the reorder.
So
here's opacity.
Right.
Yeah, so it kind of highlights or makes it a little bigger or changes the background or something.
Or if you have a progressive reveal on a web page, well, this might be less of just a client-side thing at that point. But I mean, it falls into like this general stability issue. Surprisingly, someone told me that one big difference between Google Plus and Facebook on their newsfeed algorithms is whether or not something that you've already seen in your newsfeed will stay there in the same order.
Oh, interesting. Yeah.
This is not a property of Facebook.
Right.
You can go like, oh, that was interesting a second ago, but it has now disappeared.
Yeah.
So.
Yeah, I think that's very true. I think the reordering is kind of more salient for a demo, but I actually think these subtler cues that are sort of orthogonal to the structure maybe, they're there.
Yeah. Running this on a device like a laptop is probably okay, but in the long run, when you want to, ideally this should also run on mobile phones. So, and you might, some of these pages that you mentioned might have 50 plus links. Would it actually be feasible to do this kind of reordering in real time?
Yeah, I don't know. So the answer is Web People runs on my phone. I checked that because I was curious. It doesn't run that fast. It's actually faster than I expected it to be. It's amazing what they've done with these JavaScript engines. So I think like as of now this is not optimized. This is like incredibly inefficient software that we implemented a month ago, without any attention to speed. But on the other hand, what that means is that there's a lot of speed enhancements that you can get. So I think like, over time, this will be the kind of thing that like you can do. Not of course, like this is a full language, right? Just like you can write a program that will run on the smartphone but take 3 years, you can write a probabilistic model where inference could work but doesn't. So I think there will still be the question of like there are some inference tasks that you'd rather do on the server. This particular sort of updating is actually very cheap. It turns out like you're maintaining 50 guesses about the assignment of this user to a cluster, and each time you get a click, you reweight according to the right rules. And so, it can be very quick depending on the model you have. which is an interesting thing, like just understanding which models are quick in that sense, quick for updates.
So you've been talking about speed a lot, about actually changing the UI, and I agree with this guy here that like if you change the UI, that would probably bug me. But what I would love is like predicting which link I'm going to click and having pre-cache that so that actually is a lot faster.
Yeah.
Because that's what drives me nuts. Is I'm like going on Facebook and I'm about to click on this and I know it's going to take forever. But if I knew that like just by having slowed down or something like that, some action, I know it's pre-caching in the background. It's like going to be much nicer.
That's awesome. Yeah, that's awesome. And of course, that would be it just
doesn't change anything, but makes your whole experience a lot better.
Yeah, and the way that you would want to do that is basically like allow it to expend a finite budget of CPU cycles thinking about what kind of user you are, and then just make the best guess it has at that point to cache things. Yeah. Cool. I saw this hand first.
So this feels like really similar in intent to like a personalized content recommendation system, right? How is it better?
So a big thing I want to emphasize is that this is just sort of an example that came to mind of us. The important thing is we wrote it using this very general purpose tool where you basically can put probabilistic reasoning into a web browser. So in some sense, this is content recommendation, right? Just happens to be running client side. What I think is cooler is that you now get to twiddle and come up with things. So for instance, something that we didn't have time to do, and I don't know if it would run in tractable time, is we didn't model the words, right? But I could now slap a topic model in here, right? And say that, in fact, I'm going to model the generation of the words in the link and use that as part of my inference about what kinds of things people like. Right, so I described this as people who like animals, and it did that on the basis of there were some people who always clicked on the animal links, but I can also use other sources of information like, oh, there are animal words in that link, right? And that's the kind of thing that like, you have two choices about how to do that. You can come up with that as a clever idea, spend a couple of months implementing it and submit a Chi paper, or WIST, or I don't know, one of those papers, and be like, look, we have personalized recommendation using topic models. Or you can have the Uber tool that lets you just sort of, fiddle with your probabilistic program at a high level, right? And then just do it, right? So I guess the argument is that by working on these more general tools in a way that lets you naturally run things client side or wherever, you can run it in Node, of course. We can write much more interesting models than just that one that I happened to, that we happened to implement in the last 2 days. This is super fun for me to be here. A little bit intimidating to be the first speaker of the quarter, which I didn't quite get in my head when I agreed to this date, or suggested this date. Because I'm a local speaker, I thought I would do something a little bit different than what I usually do. I'm not going to go into as much detail as I normally would if I wanted you to actually understand everything that I was saying. I want to give you sort of some details and some ideas about several things that happen in my lab with the idea that you can come down the street, walk over to the quad, and talk to us some more if these are interesting. So these are sort of various things that we do in my lab that I think are either interesting or related to HCI, or hopefully a little bit of both. And yeah, let's get into it. So the first thing is to say, what kind of thing do I spend my time thinking about? And why is it that even though I come over here a lot, I'm in the psychology department at Stanford? So here are written down as kind of examples from natural language, a bunch of really interesting ways that people think, ways that people reason. So you might hear all men are mortal, Socrates is a man, and then people would conclude, so Socrates is mortal. That's a kind of reasoning argument that people are happy with. You might also hear most men are workers, most workers are busy, so most men are busy. To us, that seems like a pretty good argument. And if you ask people, if you go crowdsource it, do experiments, people will generally endorse that as pretty good. It's different because it's not logically valid. So the systems of deterministic logic aren't going to say that that's a good conclusion. So that already sort of shows where there's a kind of genuine psychological question of how to account for the kinds of inferences people draw that our formal systems don't. You can go on and make it more interesting. Imagine a game football. Imagine that Bob beat Jim at football. You might conclude that Bob is a strong football player. But if you also know that Jim is the weakest football player, then you probably no longer think that Bob is strong. You think he's an average football player. So this is an example of kind of graded defeasible reasoning. Or something I'm going to touch on briefly as I go. I waited 1 million hours for a table at that restaurant. Probably doesn't mean that you waited 1 million hours. It probably means you waited longer than usual and you're annoyed about it. Right? So accounting for these kinds of inferences that people draw is the kind of thing that we think about in my lab, particularly sort of one corner of my lab. The other corner is we work on probabilistic modeling and AI. And probabilistic models, how many of you have never heard of probabilistic models? Okay, a subset. Oh, a significant subset. Interesting. Okay. So probabilistic models are a kind of representation structure that's come from statistics and mathematics, and that's kind of taken the world of machine learning, AI, computer vision, NLP, all of those sort of that part of computer science by storm. I'm here representing sort of in low resolution, 2 different kinds of probabilistic models that people use. On the one hand, there are probabilistic context-free grammars, which are models that describe how to get different trees, like that tree that says book the dinner reservation or something like that. And they're written down with these derivation rule kinds of structures. Over there, I'm representing what's also a probabilistic model, but that looks very different. That's a mixture model that describes the mixture of sort of 2 latent kinds of things with some observed continuous properties. So there's 2 things I want you to know about probabilistic models try to come back to at the end, something that I want your guys' help with, the HCI community. It's also a pretty good compilation target for other languages. It's a nice, simple little language that you can compile to. We have a set of notes at dipl.org on this language, and I'm going to now jump over there to sort of show you a little bit about the language. Hopefully my Wi-Fi will work, otherwise this could be disastrous. So if you go to dipl.org, oh, right, this is why I had it mirrored. Okay, at the risk of crashing everything. Yeah, oh, okay, working so far. Good. Okay, if you go to dipl.org, you'll see this, which is our sort of set of notes, a little web book. And in case you're interested in how these probabilistic programming languages actually work, you can just go read this. That way I don't have to actually tell you about it in the course of this. I can tell you what you do with them. The language that we talk about in these notes, web people, basically it's got the usual bits that you would have from JavaScript. So this is the most boring program you can write with the parts of JavaScript that we have, using pretty much all of the parts. So we can define functions. We can assign variables by calling external functions like math.exp. We can do conditionals. So this says if x is 0, be empty, otherwise stick. Do recursively call foo and stick that onto math.log of bar. Anyhow, so this is the boringest thing you could do. The point is, it just looks like JavaScript to start with. But then we start adding random sampling. So Bernoulli ERP is a primitive object that represents a coin flip, a Bernoulli distribution. And if you run it, you get a random value. Understanding the rest of this talk. One is that they're incredibly powerful, and they're powerful anytime that what you want to capture is you want to be able to represent uncertain knowledge and then describe what are useful ways to reason over that uncertain knowledge. That's why they've taken the world of machine learning and AI by storm. The other thing I want you to know is that the tools that we generally use to specify those probabilistic models are a complete mess. It's incredibly heterogeneous. That's what these pictures show you. We use some, special purpose little representations. We use some math. We use some English. We use some diagrams and pictures. And as the models get more complicated and more kind of realistic, it gets harder and harder to write them down. So the first thing that I want to tell you about is something I started thinking about 10 years, basically because 10 years ago, basically because I was building psychological models using probabilistic modeling tools, and they were very hard to write down and very complicated. And I thought there must be a better way. And then I went and realized, well, in fact, computer scientists know how to write down knowledge in a very flexible, formal way using computer languages. That's the lambda there. But what computer languages don't do is represent uncertain knowledge using probabilities. That's the P of H given D probability there. So we started thinking about probabilistic programming languages, which are basically just a merger of those two. They're a way to write down probabilistic models using the tools of programming languages. So the first thing I'm going to do is tell you very briefly a little bit about probabilistic programming languages, give you sort of a pointer to some places that you can learn some more. And then I'm going to show you an example of cognitive modeling using these languages. Then we're going to go on to do some other fun things, but we'll get there. OK. So what's a probabilistic programming language? Well, the idea is we're going to build some formal language for describing probabilistic models, starting from a universal programming language, C, Java, in our case at the moment here, JavaScript, Lisp, whatever you like. And we're going to do that by starting with the programming language, the deterministic part of the language, adding primitive functions which are random distributions, things like flipping a coin or drawing from a Gaussian distribution. Adding these two operators, sample that actually does the random sampling, and factor which upweights or downweights a particular program execution, says this one looks good, this one looks bad. And then marginalization. These are the conditional inference operators that actually describe reasoning. So in particular, I'm going to describe this to you in a language that we've been calling WebPeople, WebPPL, which is a small probabilistic programming language that's built on top of JavaScript. So it looks like JavaScript when you write in it. It's a subset. It's the purely functional subset for technical reasons that I can tell you about later. What we have in this language is several different sort of algorithms for inference, algorithms for reasoning. I'm not going to get into too much the details of how these work in here. We're just going to assume that they do work. And you can ask me later on or take a look at the things we've written. They have markup chain Monte Carlo, particle filtering, and some slightly clever search strategies to sort of actually implement the reasoning. What I like about this language, oh, by the way, it's pretty preliminary. We implemented this language about a month and a half ago when I had to teach a summer school class, and we thought, hey, why do the easy thing of using a language we have when we could write our own brand new one again? Because, yeah, that's the thing to do. So the thing I like about this language as opposed to the other probabilistic programming languages that I usually use is that because it's sort of looks like JavaScript and is implemented in JavaScript, you can use it for sort of directly embedding into web apps, which is something I'm going to